In this video, I will derive the energy of a system that consists of a very large number of particles given the partition function of the system. So the partition function Q is equal to the sum of e to the power of negative beta epsilon I. Beta is 1 over kBt, and epsilon I is the energy of the ith energy level. Using A sub I to denote the number of particles that occupy the ith energy level, we have the expression of the total energy, E, equals the sum of AI times epsilon I. Using Boltzmann's distribution, AI is proportional to e to the power of negative beta epsilon I, and then we have AI equals n, the total number of particles, times e to the power of negative beta epsilon I over q. So this term is the probability of a particle occupying the ith energy level. So if you just sum up this term from I equals 1 to I equals infinity, the sum will be 100%. And what is this n? This uppercase N is the total number of particles. And therefore, we plug in the expression of A sub I into this equation of the total energy. We have the total energy E equals N over Q times the sum of epsilon I times e to the power of negative beta epsilon I. We now derive the expression of the total energy given the partition function indirectly. So we first evaluate the first derivative of the natural logarithm of q with respect to beta. dln(q) is dq over q. This is because the first derivative of ln(q) with respect to q is 1 over q. And then we have just dq over d beta here, and then divided by q. And I'm using the expression of q, the sum of e to the power of negative beta epsilon I, and the first derivative of a sum equals the sum of the first derivatives. And then we can easily evaluate this. This part is negative epsilon I times e to the power of negative beta epsilon I by using the chain rule. So we have this epsilon I here, and we have this additional negative sign appearing here. And if you look at this expression and this expression, you will notice that they differ by just a factor of n. Therefore, dln(q) over d beta is negative e over n. And the total energy of the system is simply negative n times the first derivative of the natural logarithm of the partition function over d beta. Again, beta is 1 over kBt, and d beta equals negative 1 over kBt squared dt. So this comes from d beta over dt equals this part, and therefore we have another expression of energy in terms of temperature. E equals n times kB times T squared times the first derivative of ln(q) with respect to temperature. And for a physical or chemical system that contains molecules, we have this Q equals the product of the translational partition function, rotational partition function, vibrational partition function, and the electronic partition function. And then if you plug in this expression in here, you'll see energy is additive. The total energy is equal to the sum of the translational energy, rotation energy, vibration energy, and electronic energy.